Morning, everybody. Welcome to the Computational Social Science Seminar Series. Today we have our distinguished guest, Dr. Almaatouq, Abdullah Almaatouq, who is a Douglas Drain Career Professor at Sloan School of Management at MIT. And as a computational social scientist, his research spans roughly 3 streams, I understand. He studies and tries to improve collective decision-making systems such as small-scale teams all the way to large-scale markets and elections, examining meta-scientific questions to enhance research methods and practice, and developing research tools and infrastructure. And hopefully we will get a glimpse of those tools today in his talk. Abdullah is affiliated with MIT Center for Computational Engineering, the MIT Center for Collective Intelligence, Connection Science Research Initiative, and the Institute for Data Systems and Society. He holds a PhD in computational science and engineering and publishes broadly in general science as well as social science discipline specific journals, including PNAS, Scientific Reports, Socius, PLOS1, so behavior research and methods, and the list goes on. So without further ado, please welcome Dr. Abdullah Almaatouq.
Thank you so much for the introduction, for having me here. I was just telling Samantha earlier that actually Hongbu invited me more than 2 years ago. And the week of my visit, my little one got quite sick, so I had to cancel. And since then, I've been trying to get back on the schedule, and it's just like sabbaticals and just teaching schedules, and just couldn't work out. So I really appreciate the courtesy and the patience that you've extended towards me and really made this visit happen. I'm really happy and excited to be here today. So what I'm going to do, I'm going to have this talk that probably we'll see it's kind of choose your own adventure style of a talk. So depending on interests and questions, we can actually take it in different directions. But kind of the general plan is that there are 2 things that I want to kind of cover to a certain extent. One is some of the ongoing projects that I have on collective intelligence. So I'm going to talk about 2 ongoing projects, one about team performance, one about cooperation. I'll be a little bit lighter on the results. These are still ongoing projects, so I'm going to spend a lot of time talking about the design and some of the preliminary results. But before I do that, one thing that I want to do is to introduce what I mean by integrative experiment design, which is more of a methodological perspective that we will use in the design of these collective intelligence studies. And this approach to experimentation is something that was published earlier this year in BBS, but actually the story, so I'm not going to go into the details of what we covered in the paper, it's already out. But I want to tell you a little bit about the backstory, because I'm sure that at least some of the PhD students here would resonate with it. So this whole perspective has evolved from me being a PhD student. So this is me, first year PhD student, right? And I guess it makes that to be my advisor. And so it's a hit and miss whether this thing works. And at the time I was in the engineering school. So actually at that particular point in time, I thought I was going to be, I was in the Department of Civil and Environmental Engineering, and I was taking all of these courses that about modeling struts, joints, and bridges and physical systems in general. But then at some point I found them to be really boring, and I wanted kind of to do something with people, and instead of physical systems, to study social systems. And that's when I met Sandy Pentland, who was the director of the Human Dynamics Lab. And the pitch to him was, listen, Sandy, I'm interested in these, in mathematical modeling, in particular graph theory and networks. You're interested in human collective behavior. I can use these tools and this lens and these methods from graph theory in order to understand things about cooperation, coordination, and collective intelligence. And he was on board. He thought that was a reasonable direction, and that's how we started working together. I would go to his office. I remember in the very early days of my PhD, I would go to his office and I would have like all of these partial differential equations, trying kind of to describe how do ideas spread and what the effect of the network structure is on the spread of ideas and things like that. And then he would tell me something along the lines of, you know what, why don't you like slow down, take a step back and just do some literature review. Like, let's figure out, you're in the School of Engineering, you just decided to switch to studying social systems like yesterday. Why don't you just read about what people have found so far? What did we learn about this field? And then you will be better able to position your contributions and really frame your work and know where the gaps are so you can really address them. And that's just like a good advice for any early stage PhD student. Just like start with the literature review. I mean, it's going to be part of your thesis anyway, right? So I run back to my office and I go to Google Scholar and I literally search for networks plus collective intelligence. So I wanted to see what did we learn, and this is what we did, and this is what I found out. So if we look at something like the efficiency on the x-axis, the efficiency of the network here in terms of the average shortest path in the network, and we look at an outcome like collective performance, then there is a bunch of theoretical work as well as empirical and experimental work that would actually tell you that as you increase the efficiency of the network, right? So shorter paths between within the graph, then you would expect an increase in collective performance. And there is a very compelling theory about like rational Bayesian agents interacting with other agents, trying to estimate some signal. And from that theory, you can really derive this relationship between efficiency and collective performance. So I felt like I've learned something, right? I continue reading on that same first page on Google Scholar, and then I found equally compelling theories and papers and equally plausible explanations and as good of an empirical evidence as the other ones that go exactly in the opposite direction. So they would have a different story. The story would be about, oh, if you have efficient networks, then people can prematurely groups can prematurely get stuck in a local optimal. There isn't enough exploration. So we would expect actually a negative relationship. And there are experiments, like randomized controlled experiments, that will measure efficiency and manipulate it. And they will look at collective performance and it would corroborate that theory. So this was a little bit confusing, right? Because like, how do I put these results together? I mean, I can see it in the models that sure, maybe these models or these theories, they make assumptions if you take to be true, they render this other theory wrong. But what about the experiments? These are experiments that are manipulating the same independent variable, and they are looking at the same dependent variable, and they are reaching inconsistent conclusions about the nature, about the relationship between these two variables. So how do I really put that together? So I spent some time thinking about that. And some of my early work is actually trying to reconcile this particular seemingly contradictory result. And at some point I was like, you know what? Networks are these complicated, weird objects. I don't have the math muscle to really wrestle with it. So let me just like ditch this whole network theory approach to studying collective intelligence and just study it through the lens of something that's easier to study. So I went back to my office and I started reading, and I created this giant Excel sheet with things that people thought determined collective performance. Right? So things like the ability level of the individuals, their social perceptiveness, cognitive style diversity, team size, leadership, incentives, the task, time pressure, communication networks, which is kind of the network stuff. I had like this very, very, very long, hundreds of independent variables of things that people measured or manipulated, and they looked at the dependent variable as group performance or collective performance, right? So that was overwhelming in itself, just like trying to just figure out what is it, the things that people think determine this outcome. But then when I read about, and I dig deeper into any one of them, the same pattern repeated itself. I was able to find papers that would tell you that actually individual ability is the best predictor of group performance, to other studies that say there is no relationship between these two, to there is actually a negative relationship and the positive relationship, something else. So for any attribute, there are hundreds of attributes that matter, and for any attribute, there is evidence that it's good, it's bad, and it has no effect on the same outcome. So there I felt, by the end of my first year, I felt like I'm really stuck, because I thought by then, at least I will have like the literature review portion of my thesis sorted out, and I really can list to you things that people have found, but I really can't put them together. I was lucky that on my PhD committee, I had several of the people who generated like these results in both directions for the same attribute. So I could go there and just ask them, what's up? What happened? What do you think? Why? How do I put these two pieces of seminal work together? And the immediate answer that I got is that, in the social and behavioral sciences, we have this thing called the replication crisis, where there are some research practices that just increase the rate of false positive results in the published literature. So there are some results that are true, and there are results that are just wrong, and you're struggling to put them together because it's not that the relationship is both positive and negative, but like you don't know which one is the true one and which one is the false positive result. And that's basically just what you're experiencing right now, is just like a symptom of this thing. So I say, okay, I go back and I read about the replication crisis, and I come back to my advisors and say, listen, now I'm convinced that if I had a magic wand that I could just wave and all false positive results will disappear from the literature, I will still not be able to put these results together. And I will blame it on what I'm going to call the one at a time paradigm of doing empirical investigations. So what is the one at a time paradigm? And by the way, guys, if there are any questions here or online, please feel free to interrupt, discuss, because that also will help me manage my time throughout the talk and figure out where to spend more time. So why the lack of cumulativeness? I say it's because of this one at a time paradigm. So what is it? It starts like this. You have a bunch of researchers. They have some theory. So the theory, maybe it's like these Bayesian agents who are interacting with other agents, trying to estimate some quantity, and then you derive some hypothesis from it, like as you increase the efficiency of the network, I expect an increase in collective performance. So you have a theory and you derive from that theory some hypothesis. Then you want to kind of test that hypothesis, perhaps ideally in an experiment. It doesn't have to be, but maybe ideally, if you can, in an experiment. So you'll have to pick an experiment where you're gonna measure that relationship between the independent variable, network efficiency, and the dependent variable, something like collective performance. But when you design your experiment, there are many decisions that you will have to make. For example, one of the decisions that you have to make, where am I going to sample participants from? Are they undergraduate psych students at Yale University? Are they MBA students at Sloan? Is it a US representative sample? Is it a small scale society somewhere else in the world? Is it or is it a field experiment? So actually, I'm sampling from the population of Amazon employees because that's where I'm implementing my experiment. So there are many populations from which you're going to draw a sample. And these populations differ in their characteristics, their demographics, their expertise, their levels of social perceptiveness, their cognitive abilities. So they are different. The distribution of their characteristics are different. But you pick one, and you just sample participants from that population. But then also, you have to define a context in order for you to be able to make the measurement. So while the theory and the hypothesis that is derived from it, that as you increase network efficiency, you increase collective performance, is silent about those contextual factors, you can't make the measurements without actually operationalizing them. Things like, what is it that they are going to do? You're measuring group performance, but what is it, the task that you assign to them? How long do they have to do it? What's their incentive structure? Are they like, if they are students, maybe you're giving them grades. If they are Amazon Mechanical Turkers, you pay them based on performance. Maybe if they are Amazon employees, maybe there are bonuses or just like bragging rights. So what is the incentive structures? What is the response modality? Is it online or face-to-face? For how long will the experiment run for? So you have so many other contextual factors that will have to be operationalized to be able to make the measurement. So you run the experiment, you make the measurement, and now you have a result. So I'm depicting the color of the point as the result. So you found the blue result. I don't know, maybe blue result means there is a positive relationship between network efficiency and group performance. Maybe it's an inverted U, maybe it's an S shape, I don't care. You just found a result, a relationship between the independent variable and dependent variable on your sample from that particular population in your particular context. But if that's all you could say by running this experiment, then that's going to be a very, very boring results, right? Because it's just you're saying that in that particular sample, in that particular context, I found this relationship. But because it is a test of a theory, and it's corroborated the theory, so we believe the theory, or we increase our confidence in the theory, and then we make a general claim. We say that because we found a blue relationship in this point in the space, I say that the blue relationship holds for other populations and for other contexts. And that's why you should care about my work. And that's why I'm publishing the paper, because if you are someone who's, of course, you don't care about Amazon Mechanical Turk participants who are doing the room assignment task, but because I found this relationship in this particular place, in that particular point, I expect that relationship to hold elsewhere. So it holds for the place that you also care about.
One quick question. So, you framed this in terms of the context and population, but the example that you gave was about network efficiency, which kind of centers on the structure of the network rather than the composition of the individual's characteristics, right? So then, could there also be a way, one alternative way would be to lump the population into the context, and the x-axis would be something like efficiency or
the intervention.
Right.
It's the intervention. Yeah, I mean that's in the paper itself, the BBS piece. We talk about a different way to conceptualize, and we show that they are equivalent. We can show equivalency between them for the ease of the visual component of the framework. This will make it a little bit easier, and you will see why. So what I'm saying is that actually what we care about, it's not shown on this figure, which is the intervention, but we are picking a population and a context, and we are doing the intervention in that location. So in a different formulation, it will be a difference between 2 points, but that's fine, which is the control and the treatment. I'm saying that this is the difference between the control and treatment on that particular sample in that particular context, whatever the treatment is, the thing that you are interested in manipulating. So that's, you make a general claim, right? So you say it holds everywhere. That's you see it in the title usually of the paper, right? But we know in the social and behavioral sciences that you can't really make universally true claims in the sense that relationships between variables, they don't hold everywhere, even in physics, right? So even we know that things like Newtonian mechanics, like the universal law of gravitation doesn't hold when the objects have too big of a masses. You're talking about like black holes or things that are at extreme small distance between one another. So you're talking about the quantum level. So we know that it doesn't hold everywhere, but there is potentially a range of conditions, a range of populations and context over which this relationship holds. And typically you would see that maybe in the discussion section of a paper where they say, we found this result, but maybe this is relevant for blah, 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 blah. And then they talk about something that they might call it the scope conditions, boundary conditions, or just like some speculation about the scope of the relevance of their study. But then it's not too surprising then that you have people who are asking the same question. So what is the relationship between this independent variable and this dependent variable? But it's done by different research teams across different time scales with different populations and different contexts and finding different results depicted here by the different colors. And it's only when someone tries to come and put them together that you end up with a version of this blind men and the elephant where you have different studies about the same thing, right? Reaching inconsistent conclusions about what the thing is. And while every study touching a different part is partially correct, they are all in the wrong. And this is not new observation. So everything I described so far is what I call the one-at-a-time paradigm. actually is how we typically do science in general, not only in the social and behavioral sciences, but it has been pointed out that there is something problematic with it long time ago. So this is a paper by one of my favorite people, Alan Newell, who uses this, the way he describes the way that we do science using the metaphor of the 20 questions quiz game, where he says that the proper tactic is to frame a general question, hopefully binary, that can be attacked experimentally. Binary because you say that, I expect the control to have more of this than the treatment, right? And then you get yes or no answer. You reject the null hypothesis or not. So you get one bit of information with every experiment that you run. Having settled that bit worth, you can proceed to the next. This seems optimal. You don't risk much. There is feedback from nature at every step. You learn one thing at a time, right? And you get a feedback whether actually it matters or not. And then progress is inevitable. Unfortunately, the question never seems to be really answered. The strategy does not seem to work. We never seem in the experimental literature to put the results of all the experiments together, right? There are innumerable aspects of the situations are permitted to be expressed. That's what I'm calling the context and population, right? There are so many aspects of the situation under which you've made the measurement that are expressed that you can't even communicate or articulate or describe. So there is no way exists of knowing whether the earlier studies are in fact commensurate. So are they in the same region in the space? Do they belong to the same part of the phenomenon? Or if they are different enough that you wouldn't expect them even to replicate one another because the context and the population is different enough that it doesn't fall within the scope of applicability of that particular results. And then he was saying that each paper made a contribution. It was clear I couldn't convince myself that it would add up, even 30 more years of trying, even if one had another 300 papers of similar excellent help. So I was reading this in my office as a PhD student, 50 years later, rather than 30, tens of thousands of papers later, and it's clear that each one is making a contribution, and I still don't know how to put them together. Like this experience of Alan Newell has really resonated with me. So one thing that you might be wondering is, okay, but everything you described seems like, as you said, it's like the vanilla scientific method. You theorize, you generate a hypothesis, you test the hypothesis, and then you make a general claim. Like that's what we've learned in like secondary school on how science works. And we have very good reasons to believe that it works because we already have a lot of successful sciences that followed this paradigm. So why is it breaking here? And my answer to it is that the sciences where this method was successful are sciences or areas or domains with low causal density. What do I mean by that? So like take a physical object. So if you wanted to predict the trajectory of an object traveling through space, right? Like a planet. All you need to know to be able to predict its trajectory is the gravitational interaction between that object and a few nearby large objects. Although in theory, you know that every particle acts on every other particle in the universe, if they are influencing each other, you just say that these are higher order terms that I can ignore. I know they are acting on it, but to the level of the accuracy of our measurement, these are to the 12th degree interaction, and they are just, I can just say plus HOT, high order terms, and I ignore them and I still make accurate predictions. But when you talk about social phenomenon, things like civil unrest or team performance or attainment of a child, then there are actually hundreds, if not thousands of factors that determine that outcome. And their higher order interactions are consequential. You can't just say that, oh, the rest is high order interaction. I can just ignore and I will still be able to make prediction because these higher order interactions are consequential. Yes, all of these things matter. Anything that plausibly could affect the outcome probably does affect the outcome. And the way that they interact with each other, how their values depend on one another in determining the outcome is consequential. And we would call that high causal density. So if you were to draw the causal diagram, you will end up with so many nodes and with so many edges of how things are actually influencing each other. And once you have that high causal density, then you end up with these other consequences where we actually, if you ignore these higher order interactions, you will necessarily make wrong, incorrect predictions. So you really don't know what are the nuisance parameters, the things that the theory is silent about, but they have no effect on the outcome, and what are actually the theoretical parameters of interest, just because there are so many of them and their interactions together. So what's the alternative? And that's kind of what we do in that BBS piece. So if the one at a time paradigm isn't leading to cumulative knowledge, what should we do? We propose this alternative. And here I'm gonna go through it quickly. If you're really interested in it, it's in the paper, because I wanna kind of show how we do it in practice. And have some time to talk about that. So what's the alternative? Okay, so before we do, let's flip this process. So rather than starting from theory, hypothesis, test, generalization, let's start from generalization. So the first question we ask, what is the space? What are the range of conditions for which your theory applies or your results should hold? Or what is the space of things that you want to say something about? Right? So start from what is the space of generality that you want to talk about. So you define what are the range of populations and the range of contexts over which you want your results to hold. Then you sample from that space systematically. I'm going to talk here in principle, right? In practice, how do we do that? We'll talk about it later. But then you can sample systematically. Let's imagine, for the sake of just argument, that you can sample exhaustively from that space. Then what you will find is something that looks like this, right? So sometimes you will find the green results, sometimes you'll find the red results, sometimes it's the yellow results, sometimes it's the gray results across these experiments. But now your explanation, your theory, has to confront the heterogeneity of the findings, and then it will force people to come up with theories that, or meta theories that tells you for this range of conditions, I expect the blue results, for this range of conditions, I expect the yellow results, and for this range of conditions, I expect the green results. And then it's not a question of what is the most general result, because maybe the gray result is the most, not a few things that I want to kind of about this figure. This theory does two things. It explains the results of existing experiments, but also it makes predictions about yet unseen experiments, so that if we have an experiment there, we expect it to be gray. And also, even if you think that the gray results is the most general results, in the sense that if you were to randomly sample from the space and uniformly, then you are more likely than not to find the gray results, just because it takes more area. But actually, if you are trying to generalize to a particular situation, to your own organization, and it's actually a startup, and you work in biotech, then maybe it's this tail is the range of conditions over which you care to generalize to, and then you don't care about what's the most general results, but what are the most relevant results to any particular situation. And because it was in BBS, so we received over 30-something commentaries by colleagues, either like objecting to some of the things that we said, either in the characterization of the problem or in our proposed solution, and we get to respond to it. And so you can see the whole exchange online if you're interested. If you will read one thing of that exchange, I would say read our reply to the commentaries. I think we became much clearer in articulating the thing that we wanted to say than the original article, because we understood all of the different ways that it can be misunderstood. But unfortunately, just by looking at the number of downloads, it seems that most people just read the target article. Only the people who wrote commentaries read their own commentaries. And then it's only me who read the reply to the commentaries. But I think that's the best piece, because we summarize their perspective and our perspective on all of it. Anyway, so that happened. And some of these questions that came up you might be thinking about, like, what about unknown unknowns? Is this even feasible? Shouldn't we solve the replication crisis first? So there are a bunch of questions that, how is this different from meta-analysis? And I can come back to any of them and talk about them. But my plan for now is to address the first two, which is, okay, this sounds good. Your proposal sounds good in theory, but it's just impossible in practice. Like, how do you define the space? How do you sample from it? How do you actually integrate these results? And the second kind of criticism or objections that even if you could do this somehow, you still will not be able to address the problem. And while all of the rest of these criticisms we can have in principle, like philosophy of science, answers to them, these first two are the best way to address them is to actually do it. That will, then it's not infeasible because we've done it. And let's see whether it actually solves the problem or not. And that's kind of how I plan to spend the next hour or so of this talk. But maybe before I get into that, are there any questions, thoughts, objections? And feel free to have objections. I mean, I told you over 100 people wrote over 30 commentaries objecting to what we said. So I have a very thick skin in handling objections. Sorry, Hero, you'll be next. I think I saw his hands first. Sorry, what's your name?
Peter.
Peter, okay.
So you
maybe introduce yourself. Your name, what do you do? It's a small group. Who do you work with or what do you do? And then you can ask your question.
So I work in the kind of social network space here. We look at
PhD student?
I'm a PhD student, third year.
Mm-hmm.
So you mentioned at the start that you had looked briefly at the replication issues, but realized that that didn't account for all of the differences in results that you saw, right? So how did you initially rule that out, that it wasn't a replication problem?
It is not a replication crisis only. And actually, if anything, this framework gives you a little bit of a language to talk about it. So a replication is that you sample the same point twice and you get different colors, right? So someone ran a study under a particular, that's like an exact replication, right? Someone ran a study, they found some relationship between independent and dependent variables or cognitive style diversity increases student performance or whatever. And then someone else replicates that study. They take the same material and they try to do maybe a well-powered study to reduce the chance of false positive, and then they would try to replicate it and might not replicate. If it has a different relationship, we would say that the study didn't replicate. So the problem with, I think, replications in general, when I was doing kind of this reading, is that it was very easy to dismiss failed replications based off of hidden moderators, right? So one would come, this is a true story with a colleague of mine had a paper in Nature about something. Some other people tried to replicate it as part of that effort that was published in Nature Human Behavior that tried to replicate all social science papers in Science and Nature. And the results, and before they ran these replications, they went to the original authors. They said, okay, this is what we're gonna do. Do you agree that this is what you did? Like, do you sign off that this is actually what you did? People signed off. And then there were a bunch of failed replications. But then one of the rebuttal to these failed replications that, time has changed. When I ran the experiment, the relationship was true in 2015. But the world has changed such that now this finding, you couldn't replicate it, but you didn't, it's not an exact replication because the population characteristics has shifted of Amazon Mechanical Turk or whatever you sampled from. They used to be naive about these kinds of experiments. When I ran my experiments, now they are experienced, and that dimension that I didn't tell you about and I didn't know that it mattered back then, I think it matters and it would explain this. So you can always dismiss replication results that it's very, very, very hard, if not impossible, in the social and behavioral sciences to have an exact replication of a study. It's impossible. So all replications are conceptual replications. So basically we are trying to hit the same point in the space, but we're gonna miss. So even failed replications with the best interpretation, if we have the best interpretation that this wasn't like fraud or like some just outright false positive result, the best interpretation is that it's a failure of generalization within its neighborhood, but it's not an exact replication. So even failed replication is a special case in the social and behavioral sciences, of generalization. And that's why, like in this framework, it's like you're not, the allocation of budget of what to replicate is different. There are no, you can think of this approach is that we will not have exact replications, but we will have conceptual replications around that neighborhood of that study, and we're going to learn about regions rather than about points. But replication crisis is, as we see, is a problem, and there are a lot of things that are done there that maybe are going to address it. Pre-registration, registered reports, and things like that. I don't know to what extent they are successful in addressing the problem of false positive, and it's definitely explains some of that variability. Hero.
Yeah, fifth year assistant professor of HGI. I'm working on experiment and social sciences. So I have a question on the maybe kind of a third point is theoretical.
Third point.
Yeah. But this seems theoretical. I kind of agree with that. So that is coming back to that, to the slide you show.
Yeah, we can.
Okay, so can
let's talk about it a little bit, and then I'll come back to it at different points in this talk to tell you what I mean by theory.
Sure,
what do people mean about theory and things like that?
Because, for example, like you define, like, hey, here is a design space. I examine. Then here is the design space. Then you explore what happened. Like which design point? Maybe randomly because it's maybe too much point. Then randomly assign. So that's a great idea to think about like the examining the landscape of that. But still, for example, you show some elephant picture to that. I think it's impossible to theory say like, hey, this space has some elephant effect exists, right? Okay. So
you think it's impossible based off
from like a theoretical argument to say, for example, this x-axis, y-axis have such complex, like a complex dimension can be shown. For example, like maybe we can
be shown visually or can be characterized.
So how, for example, in social science,
and you say impossible. Sorry, I'm gonna hit on those points because maybe to give also.
So yeah, for example, like if you say like, hey, if we define this area, okay, then if within this boundary, then we can test. We will test the theory that should be like this. The landscape should be like this. Then we test it. Then we found, oh, this is true or not. Maybe we need adjustment. Then we can contribute the theory development. So that means we modify the theory to go for. That's, I think, the science works. Eventually, the theory-based idea. But here is, hey, we define, then we explore. Then, oh, we find some pattern, but we cannot explain why. Okay, so this is kind of like, okay, so it's great in the first phase of exploration, but how we can be convinced this is truth to that. So because you already defined the x and y axis or the space, maybe 3-dimensional, 4-dimensional, but you already
100 dimensions.
100 dimensions, right? So that means it's kind of like similar to say like, hey, I will work on this space, then to examine. Then try a couple of things. So even for some experiment, some people try to different settings, right?
So these are all good comments, and I wanna come back to it in light of after I show the examples, and I'll make arguments of what the role of theory is and what theory is, and we might disagree on its nature. Because one of the interesting things, there are 4 commentaries that exactly had this objection. I tell them I'm theory agnostic. They say you're anti-theoretical, but fine, I'll take that label. But 4 commentaries said this is not theory. Theory is, and none of the 4 papers agreed on what theory is. Right? So it's very clear that even if there is like some consensus on, oh, this is a-theoretical, people who call for theory, they don't agree on what theory is in the social and behavioral sciences. And that was at least clear in the commentaries that we received, and I'm happy to expand on that point. So I'm gonna have a definition of what a theory is I'll define what a theory is by its role, what it's trying to achieve. And any object that can achieve the goals of why we develop theories, then I'm gonna call it theory, and I'm agnostic to how it's generated. And that would be inclusive of all of what people suggested as theory. I'm going to be inclusive.
It's not. I don't say like it's related to theory or something like that. More likely to like this study, this type of the work is exploration.
No, but let's hold on that point, and let me talk about how do we actually do it, and then if I don't, and then let's come back to this discussion because I'm feeling we will come back to the discussion. But we will have different examples to talk about.
There's someone on, so go ahead and unmute and go ahead.
Sure. Thank you so much. I'm Nitin, and I'm a postdoc at Arizona State University. So I have a question, and perhaps if you could address this question as you go along, that would be great. But the one question I have is about the principle of parsimony that tends to drive scientific discovery and what has become like the capital S scientific method. So how do you ensure, or if you value the principle of parsimony, like simple explanations with the least amount of available info, and then layering everything on top with more experimentation by others? That is the general progression that has worked quite well until now. So how do you fold that into your argument?
I'm going to address that. Let me just say one thing. The value of parsimony in the philosophy of science as a virtue in its own, independent of its accuracy or correctness, is not really disputed. Like there is no, in the philosophy of science, there isn't an intrinsic value of parsimony. There is a value in parsimony to the extent that it corresponds to reality. But if you have a very simple explanation for a complicated thing, and the correctness wins over parsimony. And we can see that even in physics. Newtonian mechanics, you can study them in primary school, right? Mm-hmm. General relativity, it's more complicated. It requires more advanced math, but it's more correct. It makes more accurate predictions over a wider range of values. And that's why we don't take Newton to be true. We say that relativity. And then we go to quantum mechanics. And when you ask about its interpretation, what do actually quantum mechanics mean? Which interpretation do you prefer? The famous answer by Richard Feynman, just shut up and calculate. Like it doesn't matter what interpretation do you have. Like these are stories you tell yourself that gives you the subjective sense of understanding and these aha moments. But like do the calculation, look at the implication, compare it to experiments. If it gives you the biggest aha moment, but it's wrong, or you can test it like string theory, then it's not science. Right? So whenever there is a tension between parsimony and accuracy, I'm not saying that if there is no tension, then fine, you don't have to make a choice. But if there is a tension between interpretability and parsimony and accuracy, in the philosophy of science, accuracy wins. Correctness, accurate representation of how the world works takes precedence over how we feel about the explanation or the model. And I'll come back to it again a few times in this talk. So maybe Patrick, can I put maybe I want to just make a little bit of progress on the examples, and then we can address some of these questions and have these discussions in light of the more concrete examples that have their own limitations as examples of this paradigm. I mean, I would concede to that. So it's really hit and miss with this thing. Okay, so I'm going to talk about two projects. I'm going to go over them quickly because I like the meta-scientific discussions that are unfolding. So I'm not going to spend too much time on motivating the substance of these studies because I think it's even less, personally, it's less interesting. I'm more interested in the meta-scientific questions that you guys are raising. So let's take a question like, do groups outperform comparable individuals? So this is a question that has been asked in the team, in the management literature and in many fields for over 50 years. Should I hire 5 people, have them work independently, put each one in a different room, have them work independently, and then I just pick the best output or a random output from what they produce? Or should I have them, put them in one room and they produce one output? So is it 2 heads are better than 1, or is it too many cooks spoil the broth? Which one is it? And there are, let's assume, the outcome is continuous, but I'm going to specify qualitative discrete outcomes. If the group output is better than that of the best individual working independently, we're going to call that strong synergy. Group has a strong synergy if the team performance is better than that of the best individual working alone within that team. Weak synergy, it's when the team output is better than that of the average individual in the group, but maybe lower than that of the best individual in the group. And no synergy is if the group output is even worse than that of the average individual. So you put 5 people together, and what they produce is worse than if you just picked one random individual within that group and had them do the task. So how do we do this within this integrative experiment approach? So this is how we did it in practice. And you'll see in the different projects, we did it differently depending on the domain and the question. But this is how we actually did it. We went back in the literature and we looked at every study that we could find in that was published in the past 50 years. And we saw what task did they use to actually measure team synergy or team performance. And this was extremely difficult exercise, just because different papers, they mean different things by task. They don't communicate enough. They don't describe the task in sufficient detail to actually know what the task is at the same level across different papers. So it was like a very difficult exercise. But then for each, and that's just the rows of this matrix. Then the columns of this matrix is the union of existing theories about group tasks. So there are a bunch of different theories. Maybe the most common one today is McGrath tasks or complex, right? And McGrath tasks or complex kind of identifies these 8 dimensions that describe tasks, whether it's a decision-making task, cognitive conflict, generation task, planning task. So McGrath is going to be dimensionalized, and it will be 8 columns in our 24-dimensional matrix. Right? And then you have Steiner group task typology, it will be like 5 columns. So we take different theories and we say, based off of these theories, what are the dimensions that actually matter? And then we will add them as columns in this matrix. Then we ended up with this 102 rows, 102 tasks that people have used. Each task is described by a 24-dimensional vector. I'm going to call that the task space. And I'm calling the task space on the basis that any conceivable task is just a point in this high 24-dimensional space. These are just 102 points in that higher dimensional space that people have sampled in the literature, but any conceivable task can be coded so you know what are the values across these different dimensions, which are the union of existing theories. Okay, so I went through this in 1 minute, but it took us 4 years to build this matrix and an army of arrays, because again, like just sampling the rows is getting into these papers and extracting them and describing the task in a systematic way. What is the task? What the definition of a task is, and how do you describe it in a precise way was a challenge on its own. The different theories, they mean different things by tasks. Many of these dimensions are theoretical constructs. They don't come with instruments to measure them. So we have to develop instruments to actually validate these instruments. Then we can actually do the measurements. And there are a bunch of challenges such that coming to this matrix was an ordeal. And it's currently, we have a preprint just about the construction of this matrix, nothing more. Just kind of how do we dimensionalize theories and how do we actually map what people have done so far in this field.
What are these numbers? 1, 5, 3.
So it's the degree to which this task has of that dimension. So demonstrability is whether you can demonstrate the correctness of an answer. So if there is a task like an algebra problem, then before I submit our answer as a group, I can prove to you that this is the correct answer. I can verify the correctness of an answer before submitting it. But there are tasks for which you cannot verify. It's harder to demonstrate the correctness of the answer, even if there is a true correct answer during the performance, while you are performing the task. So they would vary along that dimension. Multiplicity is whether there is more than one correct answer to that task. There is multiplicity of the path. Are there multiple ways to reach the optimal solution? So you might have only one correct answer, but there are multiple ways to reach it. But maybe there is path dependency such that there is only one path to that solution. So these are all dimensions that people speculated or theorized about their impact on tasks. We just measure the extent to which each task has of these dimensions.
How are these numbers measured what it define? So it's kind of a level, right? 1, 2, 3, 4.
They are not, so these are like Holder numbers. So some of them are binary. Is there one correct answer? Some of them are the degree to which you can demonstrate the correctness of an answer was very hard to quantify. So what we did we developed a few instruments and had experts They see the tasks and they kind of label them, and then they rate them from 1 to 5. That had like low inter-rater reliability. So we actually came up with another instrument where we do pairwise comparison. So we show you 2 tasks and we ask you, this is what the dimension is, the theoretical construct. Pick the task that has more of this. And then we do these pairwise comparisons, and then we put them on a scale such that this task has more of this dimension than these other tasks. So every dimension, that's why it took us 4 years, like every dimension to quantify the number across tasks had required us to develop things to be able to do these measurements, and it varied across dimensions. Okay, so everything we're gonna do next, we're gonna do in the 24-dimensional space. But I'm going to show you 2-dimensional pictures. They are the first 2 principal components, but don't ask me if you know what those are, how much they explain of the variance, or you interpret them too seriously, because everything we're doing in the 24 dimensions. Kind of the 2-dimensional projection is just for me to derive the intuition. Can I hold your question for a few more slides, and then we can come back to it? Okay. So this is how the space looks like in 2 dimensions. These are the first 2 principal components. And you can see a few things, right? Like tasks like word construction from a subset of letters, word completion given part of a word completion given a starting letter. They are close to each other in the task space, and they are different than writing an ad, writing a story, which is similar to writing a story, which is kind of similar to summarizing a discussion, but they are different from things like recalling items from a video, recalling stories, recalling words. So all of these like cog-sci tasks are clustered in that region in the space, and they are different from something like the line dot problem. So we have now this space along which tasks could vary, and you can have some notion of similarity and differences between tasks. And now we can ask the question, do groups outperform comparable individuals? So how do we do the integrative experiment approach within the space? We pick a task. For example, we pick the room assignment task. Sorry, are you leaving soon?
Yeah,
okay, then I'll take your question.
Okay.
Sorry.
Sorry, it's just a quick clarification question about the prior slide. These tasks, these are all online experiments?
No.
Okay, so they're also like observational real-world studies?
No, they are all lab experiments, but not online, because 50 years ago there was no internet.
Right.
So these studies didn't have.
Lab experiments. So I'm wondering about the role of research studies that are doing more like contextualized real-world observations, because they often surface different dimensions or factors that could impact a given task, and that might provide some insight into the matrix that you're creating.
Very good question. Maybe I'm not gonna address it in a way that will satisfy you, I think, because I think that to address it to its depth, it will take a little bit of time that I think will extract from some of the flow, but I would love to come back to it at some point and talk to you about it. But field study tasks can be mapped into the space. There is nothing that prevent us from quantifying the 24-dimensional attributes for any task, any conceivable task. So we can map them to the space. That's just the mapping of the tasks to the space. But then, as you said, is that kind of field studies are less controlled in dimensions other than tasks, and also even lab studies. Like, I'm not saying anything about who's conducting, who are the participants of these lab studies. Are they like Amazon caricatures versus, so the population dimensions, I'm being silent about them for a reason. They are not that they don't matter. It's not that they interact with the task characteristics, and maybe teams with certain cognitive style diversity are able to perform better on certain kinds of tasks. We will study those kinds of questions within this framework, but I want to put a pin on them. And I think that's what you mean by contextual factors that interact with the task dimensions. And I'm going to come back towards the end and actually expand this to the team composition space, the group process space, and the task space, and the cross between them. But I don't want to go there yet, because that will introduce too much complexity that will distract from some of the conceptual ideas that I want to communicate.
Okay, I will read your paper and email you if I have any
Perfect.
questions. Thank you.
Call me up on it, yes.
Okay.
Okay, so we pick a task like the room assignment task, right? So we have the whole space, we pick one. So the room assignment task is just a task where you have students, you assign them to dorm rooms. they have preferences on where they want to live, they have constraints, so some of them they don't want to live together, some of them they don't want to be neighbors, and we have people come in, they do it individually, they do it in groups, and then we can compare the group to individual's performance, and we found that there is no synergy. The group is worse than the average individual in the group working alone. So now that point is red. If that's all we did, there is a theory, Steiner theory of process loss, that tells you that groups are not synergistic. And if you just run that study, you would say that, oh, that corroborates Steiner theory of process loss. And because it's a test of a theory, then I get to generalize. So I would say that the entire space is red. But actually, the knowledge you generated by running that experiment looks like that. It's even probabilistic because you have sampling uncertainty and you have measurement errors and you have all kinds of uncertainty. Maybe that the no synergy applies to the Rome assignment task, maybe other constraint satisfaction and optimization tasks, maybe other problem-solving tasks. But do you really know that that results hold in that corner in the space? So we go and we sample it. We have people do it individually. We have people do it in groups, and we found that there is actually weak synergy. So now that's a problem for Steiner because we found a counterexample, and that point is yellow. So we update our prior, and we say that, oh, you know what? For this range of tasks, and this boundary is a quantitative boundary in the task space. We say that for this range of tasks, we expect the yellow results, and for this range of tasks, we expect weak synergy. This meta theory explains why this is blue and why this is red, but also it makes prediction about all of these yet unseen experiments, that these are going to be red if we were to sample them, and they would be yellow if we were to sample them. But that's how the knowledge that we generated by running these two experiments look like. Do we think that it actually holds in that corner in the space? So we sample it. So how do we actually do this? We have two models. They don't have to be models. In this particular project, they are computational models. The first model, we call it the theory generation model. So what do we call a theory? A theory is any object that does two things. It explains existing data. It explains that the thing that we saw this red and we saw that one is yellow, it's consistent with it. It's consistent with what we observed so far. And it makes predictions about the things that we haven't seen yet. We don't care about its form. It can be in general, like we don't care about what the theory generation model is. It can be a qualitative theory. So we just send a survey to team researchers and we tell them, this is what we found so far. This is what we're going to run next. Explain what we've seen and predict what we will see next out of sample. So predict the results of the experiments that we haven't run yet. And that we would qualify as a theory generation model. If you are like CSC and really interested in the computational model that we use, I'm happy to talk about it. It's basically a Gaussian process, and the whole process will resemble active learning and machine learning and Bayesian optimization. But in general, theory is just something that explains existing data and predicts yet unseen data. And then we have another model that we call it the adversarial theory testing model. The adversarial theory testing model, it's a model that picks the next experiment and it gets rewarded if it picks an experiment such that it falsifies the theory generation model. So the theory generation model gets rewarded if it makes correct out-of-sample predictions. You predict the results of new experiments, you get rewarded if it's correct. And the adversarial theory testing model has a different reward function. It gets rewarded if it picks an experiment that falsifies the theory. And we do this iteratively, and I say until we run out of money, because actually knowing the color of each point in this case costs between $10,000 to $15,000, right? So you can run out of money very quickly, and that's where the Bayesian optimization perspective plays a role, because we can't exhaustively sample the entire space. So we have, with each point, pick the experiment that maximizes information gain. Given all of the experiments we've seen so far, what is the next experiment that will tell me the most, which is the one that falsifies the best theory I have so far? That's the point that will give me the most information. And then you end up with something like this. Some points were sampled. Some points we haven't sampled, but we make predictions about them. These are these gray points with colored borders. And we have this characterization of the space, and this characterization of the space is actually a quantitative characterization of the space that says, for this range of conditions, if you're a fan of Steiner theory of process laws, then it just applies for this range of tasks. But for these other tasks, these other corners of the space, it doesn't make the correct prediction about what the outcome should be, the relative performance of individuals to teams.
Can I ask?
Let me actually take questions now. Okay.
I'm always working with Hero,
Mhm.
HAI, and I was wondering, what do you think the difference between this framework you proposed here and the meta-analysis? And do you think, like, if you run out of sample because of money issue, do you think, like, mixing existing data from other researchers, like, what do you think about that?
Okay, good question. So this, at some point, I have some extra slides to talk about meta-analysis, but maybe this is a good point to bring it up. So what's the problem with meta-analysis? Meta-analysis is supposed to do the integration, putting things together, right? You have a bunch of people, they do their own thing, and then we come back and we put them together, and we do that through meta-analysis. So in principle, actually, meta-analysis does solve the integration problem. But the meta-analysis depends on the quality of the input, which studies you would put in. And if you have problems like publication bias, so imagine that if you have the red results, it's very, very, very hard to publish, just because no one likes these negative results. So everything you observe is only these two corners, then you would assume that, oh, the average of the current studies, the average effect is green. But because you are missing the sampling process of which study to run has been informed by the theory that it's trying to corroborate, right? And basically, so that's one. Just one is publication bias is an issue. The other one is hidden moderators. These different studies that are done on different, even all of the meta-analysis on group synergy, they can't account for the variability of the different design decisions that have been made across the studies that they weren't articulated. If a study doesn't tell you what the task is, what the characteristics of the task that they've used is, if they just give you, they don't tell you about the characteristics of the population, of the allowed group process, then these are all hidden moderators that were varying across studies that could contribute to the variance, and you can't post hoc know what the values are. So one other way I would frame what I pitched or the proposal here, think about it as a planned meta-analysis. Imagine that you say that in 5 years, I'm going to run a meta-analysis. Every study anyone runs from now until which studies should we run? And all studies will be included in the meta-analysis, regardless or not they were published, regardless or not where they found positive or negative results. We will agree on which studies to run now, and we will do the meta-analysis on all of them. Then this is just a planned meta-analysis. Patrick and then Ali, because Patrick, you had a question from earlier, so let me.
Oh, that's fine.
Okay, I will be quick. I'm Ali, fourth year PhD student at Pitt, working on intersection of higher education and future of work. I was trying to see if I can find any pattern about.
Because the background color is not real. Because even a line in 24 dimension, in 2 dimension is going to be swiggly. I'm going to show the real data in the next slide. So that's why I said in the 2 dimension, don't interpret it seriously, because everything we're doing in the 24 dimension. You can see in 24 dimension how these lines look like.
I was wondering, by any chance, you had a look at you investigated the human abilities or skills required to doing each of these tasks, and you found any pattern in any of the dimensions, the high dimensional or the projected one?
I'll address that in a few slides.
Thank you.
Patrick.
I was just wondering, those boundaries after running these experiments that you end up with, how well do they agree with the sort of scope conditions that the few publications might explicate in the public?
Very good question, and it's very hard to answer because scope conditions in the discussion sections are very qualitative in nature, and they are very underspecified. So you can't force them to make predictions. They leave a lot of degrees of freedom in the way that they are described, that it's hard to make them make a prediction. And if you do, and we tried a little bit by sending survey to experts and saying that, oh, would this fall within what you would consider? Because again, it's like they are not even wrong because they don't make risky predictions that can be falsified, at least many of them. With computational models, it's easier to do that, to force them to make predictions, but sometimes with qualitative descriptions of the boundary conditions, they are just underspecified. Sorry guys, I'm gonna grab a bottle of water and then we can continue with this. All right, so I'm gonna start introducing, we have 20 minutes and I wanna leave some time for discussions, and we haven't gotten to the second project, which I think Hero would like even more. So the actual experiment is it's a little bit more complicated than what I explained. So eventually we sampled 20 tasks from that space. For each task, we had teams of different sizes do it. So I said, oh, we compare groups to individuals, but how big is the group, right? So we tried groups of size 3 and groups of size 6. And then each task, we varied its difficulty. So when I showed you something like the room assignment task, you have students and you assign them to dorm rooms. I can change the number of students, the number of rooms, and the structure of the constraints and make it really, really, really hard to solve, or I can make it really, really easy to solve. So each task class, we have generated 3 instances that vary in its difficulty, from easy to moderately difficult to really difficult. So if you do the counting, there are 180 experiments, different experiments that we run. And here are the results. Again, these are the descriptive results because pictures and high dimensions, we can see them. But this is one of the main results, which is just showing group synergy, the weak and strong synergy across tasks for different group sizes and task complexity levels. Unfortunately, it's not showing the markers for the complexity. I'll have to fix that. But basically, the immediate thing that you see is that there is very high heterogeneity. Actually, few years ago, I published a paper in PNAS called Task Complexity Moderates Group Synergy, which basically translates to 3 points out of the 180 points that we sampled in this study. So this current study is 40 times the scope, the number of experimental conditions as the PNAS paper, but it corresponds to 3 points. The good news is that we replicated our results. So as you increase complexity, you increase group synergy, but that result only holds for the room assignment tasks. And actually you can find other tasks where there is no relationship between complexity and team performance. And there are tasks like whack-a-mole, where the relationship is the inverse. As you increase the task complexity, teams become less synergistic. And the simplest version is where teams are more maximally synergistic. So we replicated, but we also can define that this result is robust. So it's replication, but it doesn't generalize across different tasks. And similarly for any other findings. So does larger group do better than smaller groups? For some tasks, yes. For other tasks, no, depending on complexity sometimes. So the results are super heterogeneous. And actually, if we look at some theories like McGrath, tasks are complex, that put tasks in broad task categories, decision-making, planning, generation, creativity, there is as much within group variance as across task group variance, in the sense that it doesn't explain the variance in the outcome. To make that point clearer, because at every wave, so we collect the data in waves. We run, of the 180 experiments, we run 30, and then we run 30, and then we run 30, so we do them in waves. Every time, at every wave, we try to learn, we explore the space, we try to learn what predicts group synergy, and then we make the prediction, we pre-register the predictions, we put them online, we're gonna run these next 30 experiments. These are our predictions for each experiment, what the group synergy is going to be for the different complexity levels, given everything we've seen, and then we collect the data, so we can actually measure the accuracy of our prediction. And we can, for example, show that a neural network on the 24-dimensional space is able to explain almost 37% of the variance in group synergy. And group synergy here is a ratio rather than discrete. It's group performance relative to the individual or to the best individual. So we are predicting that ratio, to what extent there is synergy. So there is enough signal in the task space to explain this variance. And if we compare that to McGrath broad task categories, then it explains only 1% of the variance. But there is 40% of the variance that could be explained with these dimensions. And if we look at group composition factors, and here we have 14 attributes, so social perceptiveness of the individuals. So we do the reading the mind and the eye test, cognitive reflection tests, individual ability tests. We do the individual, relational, and collective selves test. We do the big 5 personality traits. So we do all of these group compositional factors, and they explain zero of the variance, of the out of sample variance. And this is out of sample variance, so the R square can be from negative infinity to 1. It's not bounded between 0 and 1 like in sample R square, just kind of to put this. So they are no better than just predicting whatever the average of the past is will continue to be in the future. They are no better than that. And we do like a bunch of feature importance on the neural network because people want interpretability, but it's really hard to do because actually the higher order interaction between the task features matter. If you just put in a linear model and you try to do 24 dimensions and you just do them in an additive way, then you end up with low predictive accuracy, right, with enough data. So that's 0.2 compared to 0.37 because linear models ignore higher order interactions, and higher order interactions are consequential in predicting group synergy. It's not, you just can't add those factors to one another. So we can use this to do other things. So we can generate new tasks. So the distribution of tasks in the space is based off of what people have studied in the past, but there are tasks with certain characteristics that no one have sampled. So there are empty regions in the space just because sampling of tasks has been ad hoc so far. So we can tell you that, oh, we need a task that has these characteristics. No one have studied it. So we can generate new rows. We can generate new dimensions. So this is something that we're currently actively doing. If you have two tasks that are identical in their 24-dimensional vectors, so from the lens of existing theory about what matters about the task, they are the same, but they have different colors, they have different outcomes, then this is a puzzling observation. It means that there is a latent space for which these tasks differ. And that's developing a new theory because the columns are the union of existing theories. It means that from the lens of existing theories, these things are the same. So they should have the same answer. But because they systematically have a different answer, it means that this is a puzzling observation that requires further theorization. We can examine the limits of generalizability. So if you run the integrative approach and you find the same relationship, the same color everywhere in the space, and then you find the universal law, right? So across all of the dimensions that things could vary, it doesn't matter. This relationship holds, you found the universal law. We don't live in that world. Something less than that on the limits of generalizability is that you can identify ranges of conditions over which different theories apply. I call that the theories of the middle range. So there isn't a theory that predicts correctly everywhere, but we can identify the range of conditions over which they make correct predictions. And basically, this is what we have in physics. In physics, we don't have a unifying theory for which relativity and quantum physics are a special case of. That's the goal of a unifying theory. But we have a meta theory. Tell me the scale, the speed at which the objects move. Tell me how small they are. And I can tell you whether to use quantum physics or general relativity to make accurate predictions. Right? If something moves fast, use relativity. If something is really small, use quantum physics, and I can tell you at what scale. And these theories will make correct predictions if you use them within the range of conditions for which they make correct predictions. So I will call that meta theory or theories of the middle range. Any perturbation in the context, things are so context dependent that any change to anything gives you a completely different answer. Then you are in what you can't distinguish between one of two situations that you are in. It's either all of the current theories are orthogonal to the phenomenon, so the things that you think matter actually don't matter, and things that actually matter are not included in the space. And you go back to the whiteboard and you figure out you ditch existing theories and you look for new theories. Or maybe you are in a domain for which the ceiling of predictability is so low that there is no hope for theory and generalizability. And this is a plausible world we live in, even in physical systems, right? So we have things like the nonlinear dynamics and chaos, like the double pendulum problem. It's a problem that is deterministic, for which we know the governing equations, yet we have a theory of unpredictability. We have a theory that tells you cannot predict the location, the position of the double pendulum over a long time horizon because of this path dependency and sensitivity to initial conditions. Predicting weather, the same thing. We can't predict whether it's going to rain at 2 p.m. in Boston in June 2028. We know that we can't make that prediction, and we have a theory that tells us that you cannot make that prediction. And also specifies what are the things that you could predict. So there is a paper that I wrote with James Evans. What would social science look like if we lived in this world where there is no hope for theory, where everything is just path dependent, chaotic, and nonlinear dynamics just doesn't allow you to make any predictions? What is it that we can do, and what is it that we should do? No one wants to publish that paper, so we'll see. So now I want to. I'm debating whether we just like pause and just have questions, or let me talk about the second project. I want to talk about the second project, but I'll just go very quickly through it, few minutes, and then we're gonna have discussions, because we do things differently here, so you can distinguish the things that are fundamental and the things that are just operational. Public goods game. How many people here know what a PGG is, or what a public good game is? Okay, I'm going to explain it very quickly then, just because some people will not know. It's a model well studied in economics and in behavioral economics, evolutionary game theory, and evolution as well. So you have a bunch of people, we call them players. They get an endowment, they have some income. They get to contribute to a public project, so they pay taxes, right? So they pay taxes on their income. We collected $60. We put that money into a project, we build a public school. Public school has a value that's greater than the value of what we put in the public good. And then we all benefit from having built that public school independent of what our endowment was. So this blue player, they didn't pay any taxes, but their kids still went to the public school. So they kept their money and they extracted the value from that public good. And it creates a social dilemma where the optimal thing for you as an individual to do, which is not to pay taxes, but if everyone did the rational thing, we will never build the public school, and then we are all worse off. So how do you align the incentives between the individual and the collectives? That's what a public good game is about. And I'm butchering it a little bit, but I think the intuition is fine. So does punishment solve this problem of misalignment of individual and group incentives? These studies, they say yes, punishment is good. These studies, they say no, the punishment isn't good because the cost of costly punishment outweighs the benefit. These studies, they say, well, it depends. The cost of punishment outweighs the benefit if the game is long enough. So we take this one seriously. We define 19 dimensions along which public good games can vary. The number of players, the number of people, the number of rounds, how many repeated interactions, the duration of each stage. Are you doing the decision under time pressure or not? Can you talk to one another? Economists call it cheap talk. Is it all or nothing contribution, or is it a continuous value? Do you put all of your endowment or none of it, or are you putting a continuous value? Is it by default the money is in the public good, so it's your salary is your taxes withheld and you take it out? Or is it in your pocket and you put it in? The monetary stakes, the multiplier, the cost, efficacy of punishment, the existence of reward, whether you know when the game is going to end, whether you know only your outcome or the outcome of other people. Are people punishing one another anonymously, or do they know each other's identities? 19 dimensions. So this is how the game looks like online. You're the sloth. You have $20 in the bank. You contribute. These are other people. You can chat. Everything in blue is a parameter that could vary. You contributed 15. Everyone is 26. You can punish and reward people. Everything in blue is a parameter. So you get the idea. There are actually over 6 million possible combination of parameter values. So there are more than 6 million possible public good games that you could run. So if we look at the punishment literature and we project it in that 19-dimensional space, these are where the studies are. All of these are by the same authors. All of these are by the same authors. So it's always group of 4. It's always 10 rounds. The multiplier is always 1.3, and they just vary one variable one at a time. So we run 350 experimental conditions, more than the entirety of the literature covering the space, using an algorithm to maximally cover the space with these 350 experiments. We replicate some meta-analysis results. Punishment increases the contribution of individuals, but it reduces the efficiency, the net social benefit, because the punishment cost outweighs, on average, the benefit of punishment. The cost of punishment outweighs the benefit. But it's super heterogeneous. The average effect is 1.8, but it goes from -3, a complete breakdown of cooperation, to +6, to a very maximally cooperative group. And it depends on whether the punisher IDs are known or not, whether it's a small group or not. If it's a small group and people are not anonymous, you see retaliation. You punish me for not contributing, I punish you for punishing me. But if the group is large enough, then you can't, if people gang up on you, you can't retaliate. You can't keep track of who punished whom. So it's as good as if it was anonymous, and if it was anonymous, it's the relative cost to efficacy is the thing that seems to matter. So we did that. We think we learned something by running these 350 experiments. So we're not done. So we sampled 40 new experiments, and we pre-register our predictions. So the predictions of this model, we applied on new experiments under new conditions that are randomly sampled from the space. But now we run a horse race, because people in game theory, they make predictions about this with rational choice models. People who use reinforcement learning, people who use evolutionary game theory, social psychologists use sanctioning theory. So we are running a horse race between different theoretical orientations and different models on this new 40 experiments. We already collected the data of the 40 experiments, but if you want to make a prediction, you can go to this URL, predict the results of our next 40 experiments, and you can win up to $10,000 if you are the most accurate individual. So we send this to experts, and then we're running a horse race. Which theoretical orientation can predict, and which models can actually predict, and what the ceiling of predictability is. With this, it's over 400 because it's matched conditions, 8,000 players in total, 12,000 rounds, 120,000 contribution decisions. It's all going to be publicly available. Also, we are making the whole experiment as a code available, so you can actually go and choose any parameter values you want, and you sample any point you want in the space outside of the 400 something that we've sampled to test our predictions, because we make predictions about the entire space. So you can test our prediction on any experiment of your choosing. And that's the integrative experiment. To do that, we build infrastructures. Empirica is how we reduce the cost of running each individual experiment, so we can run more of them. Some people use it. We also contribute to libraries in active learning that kind of allow you to do this active learning. So you run the experiment, you look at the results, and it will predict it will tell you which experiment you should run next, which parameter values you should select to maximize information about the characterization of the space. So we do that as well. And I'm out of time, so let me pause here, take questions, and I can hang out a little bit more and take more questions if people have time. But thank you so much for listening.
Yeah, I think we can do questions in here for a little bit, and then there's going to be a lunch.
Yeah,
so,
people if you have to leave, please feel free to leave. And if you have
so
questions,
you're all
then
here all day and 3:10. So for people meeting.
So if I make predictions there, am I also part of an experiment?
maybe a meta-experiment that we're not part of. So this is, who knows Social Science Prediction Platform, SSPP? Okay, so it's a platform managed by someone at Berkeley. When you design a study, before you run it, they allow you to post, they run competitions like forecasting competitions, and they have super forecasters, people who predict the results of all experiments. And to be in that group, you have to be accurate in predicting the results of social science experiments. So you get there, you can put in the design of your experiment there, and they will do all of the data collection, contacting the experts, managing the identities. So we don't know who the experts are, but maybe you can opt in if you want to win prizes to let them know what their accuracy, and they can do that. They can analyze how accurate people are across different studies. For us, from our purpose, we just care about our own study, what experts' predictions are, and we have lay people prediction, and we can like have benchmark model predictions and things like that. But maybe they are running their own experiments at the platform level. I don't know.
Hi, I'm Qing from postdoc at University of Pittsburgh. Work with Morgan on the energy transition and labor market. So I have a question on the matrix. Conceptually, I understand it. It's very hard to, when you construct a matrix, you are still rely on the existing knowledge, which also suffer the publication bias.
Very good question. Let me address that, because that's a very important one. So one thing I want you to notice is that across the two projects, we came up with the dimensions differently. In the first project, union of existing theories in the literature. In this other project, because public good game is very stylized, we can actually read off what are the dimensions. So there are dimensions that no one theorized that they matter. We include them anyway, and then it's an empirical question. But what is the design space of these experiments? The design space at any point in time is our best guess for the things that matter in determining the outcome. And that best guess gets refined and improved with empirical feedback. So as we sample experiments, so I showed kind of an example to it, but I didn't make that leap. When you sample experiments and you have 2 points on top of each other that have different answers, then you need to add a dimension. So that's a dimension that's missing from the literature, and we can tell you which observation you have to pay attention to be able to develop this new theory. But also we do it in the other way around, which is there are dimensions that Steiner said it matters, and we vary experiments across that dimension, and it doesn't vary the outcome. And then we drop that dimension. So the dimensionality of the space, also I said 24, it's not fixed. As we run experiments, it's expanding to account for unaccounted for variability in the data, and it's contracting when we vary it along dimensions that are not varying the outcome. So the space is always expanding and contracting in response to feedback from running these experiments. So in different domains, the construction of the design space will look different depending on how many established theories are there and whether people agree on them. That's why it's easier to do it with the public good game than to do it with the synergy project. So it will vary from one domain to another, but at any point in time, it's our best guess. That's why we put all our predictions online. You find an experiment that shows that we're wrong, we will update either our characterization of the space, but depending on how we are wrong, maybe it's more dimensions or less dimensions. That's fine.
So really interesting talk, and I'm really excited to see what comes out of this paradigm in the long run. I just wanted to get your thoughts on where this might go. So you can imagine two, opposite directions. One is the more emergentist. So I'm thinking, when we're thinking about individual behaviors, an emergentist sort of view would be to look at larger units that consist of individuals. Or if you're going the reductionist route, you're thinking in terms of the individual psychology. If you go even further down, you can go all the way down to the atoms and physics. That would be the reductionist. So in this setup, which way do you think this will lead you to?
So I think the framework is agnostic to the unit of analysis, right? Because I showed 2 projects, but we have 2 more. I happen to be someone who is maybe more on the macro outcomes people, but in one project with cognitive scientists, we are actually doing risky decisions under uncertainty. So you have gambles, and you pick A with certainty, you get $1, or B, 50% chance you get $10 or something like that. And we can vary the parameters of the number of options and the distribution of characteristics, the stakes and things like that. So we have dimensions to vary, and that's just doing it at the individual level decision under uncertainty, and we do it in the same exact framework. But then we have different kinds of theory: rational choice, expected utility, prospect theory, and you kind of, but that you kind of run a horse race between them, but it's at the individual level. I tend, for historical reasons, just path dependence, that I do macro level things. If anything, it's been difficult and it's expensive to experiment at that unit of analysis. So maybe it's better for me to switch and study individual level stuff if the point I want to make is more meta-scientific about the approach rather than any particular domain, because I'm not, the Synergy project just like drained a lot of time and energy and resources for reasons that are orthogonal to the meta-scientific points. Just like people in that field, they don't agree on what a task is. They use different words to mean the same thing. They use the same words to mean different things, and just kind of, there's another mess that you have kind of to figure out to be able to start. And it's just like an accident of history that I found myself there. So that's kind of about the unit of analysis. It's agnostic, I think, about how it will do. I thought you were, with your question, there's a kind of another way to see how I envision this is going, which is kind of related to, does this mean small labs can't participate? I said, sampling each point costs $10,000, $15,000, and we are doing it now in hundreds of points. We're spending literally hundreds of thousands, or if not millions of dollars across these projects of just not labor cost, just human subject cost. So there is kind of this shift in calculus, how much a project costs in terms of human subject cost, and then the labor cost that I are to do the research. And my view of it is that eventually it's going to be distributed. So we started trying to be distributed in the sense that we, 5 years ago now, we had a meeting with a bunch of people who are interested in group performance. I said, listen, let's define all of these dimensions along which our studies can vary. Each person run your own experiment in your own corner in the space, publish your own paper, and then in 5 years we will write a community paper where we put everything together. Even null results will be included. Even if you don't get to publish, it will be included. And then you have your own individual paper in your own corner in the space, but also we can put things together at that. People loved the idea. During the meeting, it was impossible, or it felt impossible to get them to actually contribute to it afterwards, because like, why would I be a cog in someone else's machine? Why would I pay this extra cost that doesn't benefit me? Community paper, how many authors? 100? The first thing people are going to do in my promotion case is just strike the citations from that paper. So it's like, there is no incentive for me to do it. So it was really hard. So my view was, let me do it. Let us do it first, show its value, and then something is going to happen that will allow it to be done in a more distributed, collaborative, large science way.
Oh, we're just gonna let
Yeah, I think
people
there's
come in,
another
but continue talking,
So,
there's gonna be more people.
Yeah, I'm just trying to imagine what a scientific result is going to look like in this world as it proceeds. It kind of sounds like for any phenomena we want to explain, the result is going to be some evolving multidimensional set of regions where the number of dimensions will change over time. The regions will change over time. So yeah, in the middle ground, I assume everything's going to end up in the middle ground. I don't think we're fine-tuning universal laws, and hopefully we're not going to find total chaos. So, I mean, is that sort of what science is going to look like? Or do you imagine that within each of these regions, there'll be sort of a, I don't know, mosaic of theories that will explain region by region? Or what will it look like if this moves forward and is successful?
The optimistic view is that it will look something like this. So for example, if we want to predict human behavior in making risky decisions, we say in these range of conditions, they act like an expected utility as economists predict. In this other region, when the characteristics of the situation, of the context and population has these characteristics, then they act like prospect theory. And then they have all of these aversions and irrationalities. And if it looks like this, then they act like reinforcement learning. And then we define these regions for which different explanations would apply.
So there will be kind of a theory for each region, or a
yeah, because in the extreme case, when theories are very narrow in scope, the extreme case becomes like that. between this and this is like a degree, right? It's like from universal laws to no hope for theory, and it's different domains and different questions will fall in different values on that generalizability line. And then at some point, maybe it's not worth it to come up with theories because they are so narrow in the range of conditions for which they explain stuff that the value of a theory, which is generalizability, is kind of not worth it.
Yeah, super interesting. I'm really curious to see where this goes.
Thank you so much.
Thank you.
Thank you.